already past 5. So thank you for all of you for joining us today, despite feeling so exhausted and only having finished exams today, etc., etc. It's really nice to have all of you here with us. We are continuing our exploration of the rules of differentiation for calculus. And after our first lesson, we managed to cover what the basics of first principles and some really sort of simple differentiation questions, so ones with one term. So today what I wanted to do is just go and have a look at those that have got more than one term, so function statements that have got more than one term, and also what happens when we have a monomial denominator and what happens when we've got a binomial denominator. And then the other thing that we're going to look at is what happens when we've got brackets and roots and divide lines. Okay, so we're going to talk about all of that this lesson. I've got some really nice difficult questions for you guys to try at the end. If we don't get to those this lesson, then we can always try a few in the next lesson as well before we try the exam questions. Okay, so let's just jump straight into it. Example number 1 really is sort of the most basic, simplest example that you could probably get. And I would say probably in all of your exams, a question like this would be like the first one where they're asking you to apply the rules to find the derivative. So something really nice and straightforward. If you recall from the last time, if we want to derive, we want to write each term, sign, coefficient, variable in the numerator with our exponent. And then that allows us to apply our power rule to each term. Okay, so remember our power rule means we are multiplying our exponent by our coefficient and subtracting 1 from our exponent. That's our power rule. And then the other rule that we have to be aware of is that the derivative of any constant is always 0. Okay, so how would we apply that to example number 1? Well, as follows. What we want to do is look at the statement first and decide, is it ready for differentiation? Okay, can I clearly see each exponent? Are all the variables in the numerator? Can I see what the exponents are? And if the answer to those questions are yes, then you can go ahead and go and apply your power rule. Okay, so that means I'm going to write f prime x. And I'm now going to end up with 2 terms. I'm going to end up with 4x cubed plus 6. And that, yeah. Thank you, Cassandra. Well done. That would be it. All right. And what they would do, especially with something like this, there would just be a mark on each one. Okay, simple and straightforward. Okay, now let's have a look at example number 2. Now, I'm doing this on purpose because, and I'm sure your teachers would have mentioned this to you at school, but I just want to sort of emphasize this point as well. You cannot differentiate with respect to more than one variable at a time. So if you have a look at example number 2, right, if they didn't tell us that p was a constant, we could not differentiate with respect to x and p at the same time. So either we must differentiate with respect to x or we must differentiate with respect to p. So if we were going to differentiate with respect to p, then over here, instead of it being dx, it would be dp. All right, and if you want, what I can do is I can show you how we would differentiate with respect to p, and in this case, p would not be a constant. Okay, so in the question that we are doing here, they have said to us that p is a constant. All right, so p represents a number. All right, what is wrong with this? Well, not wrong with it, but the problem is that this is in the denominator. All right, so remember, we're not allowed to have variables in the denominator if we want to derive. So we've got to get rid of that divide line. Because I am not deriving yet, I've got to write dx in my square brackets. And I'm going to write px squared plus p squared. And then what am I going to do with that last term? How am I going to write x squared so that that x is in the numerator? Can anybody tell me?
Ma'am?
Yes, Cassandra?
Can I say x to the power of -2?
Lovely. Okay, so plus x to the power of -2. Good job. Okay, and of course, 1 times x to the power of -2 is x to the power of -2. All right, now, are we ready to differentiate? Yes, okay. We've got rid of the divide lines. We can clearly see each exponent as well as each coefficient, even if they are invisible ones. And now we can go ahead and go and apply our power rule. Remember, we tell, or the way that we indicate that we are applying our power rule with this kind of notation is that we drop the dx and we drop the square bracket and we just write equals. Okay, so what is our first term going to be in this case? Does anybody want to say? What do you think it would be?
Yes, ma'am.
Okay, Moronkoa?
It will be 2px
It will be. Keep going. I like what you're doing.
plus p.
Plus? This
Plus
is a 2
sorry.
plus 2p.
Sorry.
Awesome. No, no, no. Don't say sorry. No problem. Keep going. Lovely.
Minus 2x to the power -3.
Lovely. Okay. Very nice. Well done. Okay. Good job. Everybody happy with that? Okay. And of course, you can leave your exponents as negatives. All right, you do not have to then go and rewrite it as a positive exponent like they expected you to do in grade 9, 10, and 11. Okay, lovely. Well done. Thank you so much. All right, now let's just talk about differentiating with respect to p. Okay, so now in this situation here, when we differentiate with respect to p, p is not a constant. Okay, so in this situation over here, p is not a constant, right? So essentially what we've got, if we're differentiating p with differentiating y with respect to p, what our x's are actually going to end up being our coefficients essentially. All right, so we would need to do the same thing, right? But what I would probably do here is I would switch it around and I would write it as x squared p plus p squared and then plus x to the power of -2, like so. All right, again, I'm ready to differentiate because I've got my coefficients, my variables in the numerator, and now I can go ahead and go and apply my power rule. All right, so what is going to happen? Remember, we are differentiating with respect to p. So what's going to happen to our first term? What's our first term going to be? Does anybody know? X squared is now our coefficient. All right, so we're going to take the invisible 1 that's up here, and we're going to multiply it by x squared. That's going to give us x squared. Then remember, we've got to take 1 away from our exponent. So it becomes p to the power of 0, which would be 1. So it would be x squared times 1, so that would be x squared. Is everybody happy with that? Is that making sense, Matrix? Yes? Okay, good stuff. Okay, and the next term. Okay, remember, p is not a constant now. So the next term is going to be?
P.
2p. All right. What we would have had to specify here, okay, as far as the x to the -2 is concerned, what would happen to that?
It will stay the same, or it will be equal to 0.
Which one do you think, can you see there?
0.
Okay.
We don't have...
Okay, so in this situation here, if we are treating x as a constant, then yes, it would be equal to 0. Okay. So it depends on how we want to treat x. If we are treating it like it is another variable, so we would have to define here, I suppose, before we got started, whether x was a constant or not. But let's say x is a constant, because that's probably would be easier for us. X is a constant. Well, actually, then we wouldn't have ended up with what we had over here. So actually, let's not treat x as though it's a constant. If x is not a constant, then we would have ended up with the exact same thing. All right, so we would have ended up with plus x to the power of -2 as part of our answer. Okay. So the reason why I wanted to do this example with you is because you cannot differentiate with respect to more than one variable at a time. Okay, so if you do want to differentiate, it can only be with respect to one variable when you're applying your rule for the derivative. Okay, let's go and move on, and let's talk about functions that have more than one term in them. All right, so important things to remember when we are differentiating. You need to remove brackets, divide lines, and root signs. And when I say root signs, I mean from variables. If you've got a root sign on a constant, you don't have to get rid of that, but you have to get rid of root signs on variables. So what I'm referring to here is if you have got something like the cube root of x squared, all right? So you are required to write that as x to the power of 2/3. Remember, the guy at the bottom gets bounced to the outside of the party. When we say divide lines means, again, when variables are in the denominator. So if you've got something like 1/2, no, let's change that. Let's say you've got x squared over 2, all right? Because the x squared is in the numerator, that's fine. What we would do here is we would write it as 1/2. So we still got the divide line there with a number, but we've got the x squared in the numerator. If you had something like 2/3x squared, then when I'm saying you need to remove the divide lines, what I'm trying to say to you is that you would then have to take that and write it as 2/3x to the power of -2. Okay, so it's the variable that has to be in the numerator. Brackets we want to get rid of because we need to have terms and not factors when we are differentiating. So the first example that I have given you is this easy one over here. So f of x equals 4 minus 3 squared. So we are not differentiating first. We are removing the brackets. So I'm going to write f of x. And then I'm going to square my binomial. So I don't know if you remember that rule where we square, double, square. All right, so that's going to give us 16x squared. Our middle term is going to be -24x, and our last term is going to be plus 9. Now that we've got rid of the brackets, we are essentially where we were at the start of this lesson with a question like that one, and now we can go ahead and go and apply our power rule. So we write f prime x, and that would give us 32x minus 24. Okay, everybody happy with that?
Yes, ma'am.
Okie dokes. So now I'm giving you guys 2 to try, all right? C and D, is that big enough? Can you see them okay?
It looks good.
Does it? Okay, all right. So you guys do C and D, we'll mark it, and then we'll move on to the next thing. Cool, Johannes, well done. Well done, can you see there? Nice, Selma. Okay, well done, Matrix. I'm just going to wait 1 more minute and then we can mark it and move on. Okay, that's it. Our minute's up. Nobody else has put down into the chat. Hopefully I've given you guys enough time to get through it. Let's go on with the answer. All right, so hopefully in question C, you realize that it was ready to be differentiated as it is, and you would have ended up with, so 6 times a third would have given us 2x, and then that would have been to the power of 5. And then over here, it would have been minus 6x to the power of 7 minus x to the power of negative 3. If I'm not wrong, did you guys get that answer as well?
Yes, ma'am.
Yes, ma'am.
Good. Okay, well done, everybody. So that one wasn't too difficult. And then as far as the next one was concerned, here, lovely Thelma, thank you very much. Here you would have first had to remove the brackets. So again, very important that you write y equals and not dy over dx. So this would have been x squared plus 2x plus 1, and then the derivative of y with respect to x for this question would be 2x plus 2. All good?
Yes, ma'am.
All right.
Sagwadi, would like you to explain again, please.
Okay, which question? Both of them. Just have a look. Which one, Sagwadi?
Can you please explain C, ma'am?
C. Okay, what did you specifically not understand, Sagwadi? Where did I miss you or confuse you or?
I was looking at the notes from the last class, and I can't really understand how we got to.
Okay,
that
so
answer.
what? Okay, so what I'm doing is I'm applying my power rule to each term. So I'm taking my exponent. So in the first term, my exponent is 6, and I'm multiplying it by my coefficient. So 6 times 1 over 3 is going to leave me with 2. That's where the 2 comes from. And then I've got to take 1 away from 6, and that's where the 5 comes from. And then it's the same story with the 8. When I apply the power rule to the second term, I'm taking 8 and I'm multiplying it by negative 3 over 4. So here, what would happen is that 4 would go into itself once, it would go in there 2 times, and 2 times negative 3 would leave me with negative 6. That's where the negative 6 comes from. And then again, I'm taking 1 away from the 8 to get an exponent of 7. And then with the last term, I'm taking negative 2 and I'm multiplying it by a half. That's where the negative 1 comes from. So the invisible negative 1. And then again, I'm taking 1 away from the exponent, and that's where I got the negative 3. Does that make sense?
Yes, ma'am. Thank you.
Okay, pleasure, pleasure, pleasure. Okay, so now here we've seen here we see something that we haven't seen before, all right? And what we've got here is a monomial denominator. Okay, so one term in the denominator. What's important to note with questions like this is the following. If I have 1 plus 2 plus 3 all over 7, what does that mean? It means 1 over 7 plus 2 over 7 plus 3 over 7. So when there is a monomial denominator, we are going to split the numerator over the monomial denominator. I am not dropping my dx, I am not dropping my square brackets because I'm not differentiating. I'm getting my function statement ready for differentiation. So I will now split it up and write x squared over 2x squared minus x over 2x squared minus 6 over 2x squared. Now it's essentially like you were when you were in grade 8 and when you were dividing like terms, you subtract your exponents. It's exactly the same idea. Okay, so again we can write equals dx like so, and here x squared divided by x squared would leave me with 1. So the first term would be 1 over 2. I hope that makes sense to everybody. The second term, I would end up with 1 over 2x, because x at the top would go into itself once and would go in here x number of times. And then as far as this last term is concerned, 6 divided by 2 is 3, and that's 3 over x squared. But I'm not ready to differentiate because I cannot have my variables in the denominator. So I have to move them to the numerator before I differentiate. So I'm keeping my dx, I'm keeping my square bracket, and I'm writing 1 over 2 minus, and I'm separating the coefficient, taking the variable to the numerator and changing the sign. Okay, and again thing here, I'm separating the coefficient, taking my variable to the numerator and changing the sign of my exponent. Now I am ready to differentiate. Okay, so getting rid of divide lines means for the variables. Okay, so you can still have a fraction with a divide line in it as a coefficient, but you can't have a variable in the denominator. Okay, let me just move this one down because that's for you guys to try. All right, now, am I ready to differentiate? Yes, each term is written, sign, coefficient, variable in the numerator with my exponent. I indicate that I am deriving by dropping the dx and the square bracket. The first term is going to become 0. Okay, second term, minus 1 times a minus half is a positive half. Take 1 away from the exponent. Third term now, negative times a negative is a positive. 3 times 2 is 6. X, take 1 away from the exponent. I'm going to end up with negative 3. All right, so a question like this could be worth, I'd say probably about 3 marks. There would definitely be, or maybe even 4 if it was a class test or something. There would be a mark on each one of those. There would be a mark for splitting it up. And if there was another mark here, there might be an accuracy on that line. Okay, does that make sense to everybody? Any questions? Okay, good stuff. All right, now you guys try this one. Okay, good. Can you see there? Thank you, Thelma. Nice, Moranfoa. And Artile, good. Thank you, Maite. Nice, Neo. And Johannes, lovely. Good job, guys. Cool, Valerie. Nice boy, chair, Paul. Okay. Good, Boucher. Okay, so they are asking us to derive with respect to t. So in this case over here, we are having to split this up first. So we would have ended up with t cubed over t minus t squared over t plus 1 over t. We're not ready to differentiate. We've got to get rid of those divide lines. So in our next line, we're going to end up with our first term being equal to t to the power of 2, because when we divide like bases, we subtract our exponents. Second term is going to be minus t, and then this one is going to be t to the power of -1. Okay, now we're ready to differentiate. Dropping our dt, dropping our square brackets, we're going to write 2t minus 1 minus, whoopsie, t to the power of -2. How did that go? Good. Nice one, guys. Well done. Where did we get -2? So remember, you've got to take 1 away. So see, Claire, you've got to take 1 away from the exponent. Okay, after you have multiplied the exponent by the coefficient, you've got to take 1 away. Okay, so -1 minus another one is -2. Okay, see, Claire? Okay, I'm hoping that's okay, Cecily. All right, moving on to the next example. What's different here? How is example number 5 different to the previous examples? No, Cecily, it's not the second derivative. Hang on a second, let's just go back here. No, it's not the second derivative. We're only taking the first derivative. Okay, but because our term is plus t to the power of -1, we are saying -1 times the invisible one that stands in front, and that gives us -1. Okay, so that gives us -1. And then from here, we're taking away 1. Okay, so that means it's going to be -1 minus another one, which is -2. Okay, see here? So we only take the second derivative when we're working with the cubic function, or if we're doing min-max problems and like there's a question about acceleration, or where else would we take the second derivative? Yeah. But yeah, we're not taking the second derivative here. It's just the first derivative. Johannes, I love it. Okay, factorize into 2 brackets. Absolutely. So the major difference between function statements with a monomial denominator compared to a binomial denominator, when you have got a binomial denominator, you have to factorize. Okay, just as Johannes said. What else do you have to do in this particular example? do you think? Apart from factorizing. Anyone got any ideas? There's something else that you need to do. If you look at the bottom, it's written as 3 minus x. Okay, so that means that we're also going to have to take out a factor of -1. Otherwise, our brackets are going to be the wrong way around. Okay, but before we get there, if we look at the top, we can see that we can take x out as a highest common factor. So that gives us 3x squared minus 7x minus 6. All over, and now I'm going to do my switch round. So I'm going to take out -1, and then here I'm going to have x minus 3. Does that make sense to everybody? So that was the switch rounds that you guys learned how to do when you were in grade 9, grade 10, when you take out a factor of -1. All good? Now we have to factorize our trinomial. It's a complex trinomial. So 3, fortunately, is a prime number. So this is going to be 3x. This is going to be 1x. All of this is over minus x minus 3. And now we've got to figure out what factors have got to go into our second term. All right, so now we're thinking about the factors of -6. So the easiest way for you to do this, if factorizing is a challenge, is to write 3x times x to give us 3x squared. Now we've got to think of the factors of 6, that when we subtract them, we're going to end up with -7. So the best thing for you to do is start off with numbers that are closer together. So as far as 6 is concerned, you can get 6 by multiplying 1 and 6 together, or by multiplying 2 and 3. 2 and 3 are closer to one another than 1 and 6. Okay, so let's go with 2 and 3 first. If you cannot take out a highest common factor from the trinomial, then you cannot put multiples of the same number together. So in other words, what I'm trying to say is if I'm using 2 and 3 as my factors, I cannot put 3 up at the top here. Because if I did that, I would need to be able to take 3 out of every term, and I can't because the middle term is 7. So if you know that, it kind of gives you a bit of a head start here, because you would immediately say to yourself, well, if it is 2 and 3, it would have to be like that. Okay, so you start at the top and you come down, and you start at the bottom and you go up. And can 2 and 9 make -7? Yes, go back, fetch the middle term together with its sign, and that will tell you what needs to be negative and what needs to be positive. So now we're working with integers on a number line. In order to get -7x, we have to start at -9 and add 2, and then those signs go straight across into the brackets. Okay, so that one will be plus and that one will be minus. Okay, so plus 2 here and x minus 3 there. Okay, and we were expecting that, because what would be the point of having that denominator if we couldn't cancel it with a factor in the numerator anyway? Is everybody good with that? Does that make sense? Cool.
Yes, ma'am.
Good stuff, Cassandra. Okay, and now, Matrix, you are going to cancel factors. So that factor at the bottom with that factor at the top. Don't forget, you've still got this minus floating around at the bottom. Okay, so if you take x times 3x plus 2 and you divide it by -1, it's the same as multiplying it by -1. So that means we're going to end up with dx, and here we've got -x, and we need to multiply that by 3x plus 2. Okay, remember we've got to get rid of brackets. Let's move this one down. Okay, so now getting rid of the brackets, we're going to end up with dx. Okay, minus 3x squared minus 2x. Are we ready to differentiate now? Absolutely. Okay, drop the dx, drop the square brackets, just write the equals and apply our power rule. So 2 times -3 is -6. take 1 away from the exponent. So now it's x to the power of 1. Invisible 1 times negative 2 is negative 2. Take 1 away from the exponent. And now it's times x to the power of 0, which is 1. Okay, everybody happy? And there's our final answer. Nice, well done, everybody. All right, cool. Now here's one for you guys to try. Okay. Cool, Cassandra, well done. And Neo, lovely, good job. Lovely, well done, Matrix. Cool, Buhle, well done, Maite. Do you want to pop an answer into the chat, Matrix? What did you guys get? Cool, thanks, Kanisile. Anybody else get an answer they're really willing to share? Don't be shy, guys. Okay, so Sihle, you got some, Mighty, you got 2. Sihle, okay. Buhle, Cassandra got 2. P, Neo got 2. Okay, all right. So most of you are getting 2, but some of you are getting slightly different answers. All right, so no, ma'am, 2. Okay, Cassandra, cool beans. So here would have been 2p plus 1. Here it would have been p plus 1, like so, all over p plus 1. All right, that would have cancelled with that. And then here you would have ended up with 2p plus 1. And that's why you're all correct in saying that the answer would be 2. Okay, good. Yes, certainly it would be. Okay, nice. Well done. Everybody happy? Okay, now let's move on to something a little bit more challenging. Good stuff. Okay, how are we going to deal with this? Okay, so here we've got to remove a divide line, but we've also got to remove a radical, okay, or a root. So the best way for us to deal with something like this is don't panic. All right, think clearly. All right, we've got to remove divide lines and we've got to remove radicals. All right, so y is equal to, notice I'm not writing dy over dx because I'm still preparing my function statement for differentiation. So what I'm going to do is I'm going to kill two birds with one stone, as we like to say in English, and I'm going to remove the radical as well as split in one step. Okay, so I'm going to write the first term as 2x squared over x to the power of 1 over 2. Does that make sense? And then again, I'm going to get good stuff. I'm going to get rid of the radical. Not that it's really going to make much of a difference in this particular case, but anyway, that's fine. And then I'm going to do the same thing over here. All right, I'm going to split it up and I'm going to get rid of the radical. Okay, now I've got a little bit of simplification to do. All right, this is just like when you were in grade 8. Okay, when you divide like bases, you subtract your exponents. So y equals 2 divided by 1 is 2. Keep my x. And now when I've got 2 minus a half, what's that going to leave me with? 2 minus a half is?
3 over 2.
It is. It's 3 over 2. Okay, good job. Minus anything divided by itself is 1. Okay, and then again, remember with the last one, we've got to remove the divide line for the variables. Okay, so 5 is happy. It's at the top. X goes up to the top and it changes its sign. Okay, now you're ready for differentiation matrix. Okay, because each term has been written, sign, coefficient, variable in the numerator with your exponent. Okay, so now we can write dy over dx, the derivative of y with respect to x. And now we've got to multiply 3 over 2 with 2. So 3 over 2 with 2 times 2 is 3. And I've got to take 1 away. So I'm going to end up with 1 over 2 as my exponent. Minus 1 is going to become 0. So that term is essentially not going to be there anymore. And now a negative times a positive is a negative. 5 times a half is 5 over 2. So remember, it's okay for me to have divide lines with numbers. And then I'm going to write down my x and I'm going to take away 1. Okay, so that's going to leave me with an exponent of negative 3 over 2. Does that make sense, everybody? Any questions?
Ma'am, could you please explain what you did with the -1? I missed that, ma'am.
That's fine. So Kumo, -1 is a constant. So the derivative of any constant is 0. So I'm not going to write 3x to the power of a half plus 0 minus 5 over 2x to the power of negative 3 over 2. If I've got 0 as a term with other terms, then I don't write 0. Does that make sense?
Yes, ma'am. Thank you, ma'am.
Okay. It's a pleasure. Any other questions? Okay, good stuff. All right, so then in that case, let's go on and do the next question. So this is for you guys to do, all right? So you're going to determine the derivative with respect to x, and here I've given you one with a bracket and a radical. Okay, so you guys try this one quickly, and then again, when you're done, just pop down into the chat and then we can talk about the answer. Cool, off you go. Cool, Marty, well done. That was quick. And Neo, nice. And Sihle and Morangoa. Wow, lovely. Well done, Matrix. Good, Johannes. Nice, Kanisile. Cool, Valerie. Good, Lucidi. Well done, Thelma. Not to our Matrix, Nicole. They eat radicals for breakfast. Okay, cool. Let's smash this guy. All right. So if I was doing this question, this is what I would do. I would write root x as x to the power of 1 over 2. And then I think I'd keep my brackets for now, and I'd move the x to the power of minus, or x to the power of 4 into the numerator. So I'd separate the coefficient, move that guy up to the top, get rid of my brackets. So now when I multiply like bases, again, it's grade 8 work. When I multiply my bases, like bases, I must add my exponents. Okay, so I'm adding 3 to a half. That is going to give me 7 over 2. Okay, and if you're not sure of that, that you can do on your calculator. No one's going to stop you with it. Again, when you multiply like bases, you add your exponents. So now when we're distributing, we've got 1 times a half is a half. Keep my x. And now when I add my exponents, I'm saying half plus minus 4. So that means I'm going to end up with a half, take away 4. So I'm just doing this quickly. So that would be 1 minus 8 over 2, which would leave me with negative 7 over 2. Okay, if you want to work that out on your calculator, there's no problem with that at all. Are we ready to differentiate? Yes. Okay, so again, we've written everything. Coefficient, variable in the numerator. We can see what our exponent is. Now we're ready to apply our power rule. Okay, so the derivative of y with respect to x
I'm
is...
sorry for interrupting, ma'am.
Yes,
But
no
ma'am,
problem.
Why didn't you let the 2x to the power of 4 be the numerator and then the negative 4 changes
Okay,
to...
because... Okay, but you see, the thing is that the coefficient is 1 over 2. So the 2 is going to stay in the denominator. It's only the x to the power of 4 that wants to move to the numerator.
Oh, thank you, ma'am.
Okay, absolutely, no problem. Okay, so now applying our power rule, that would give us 7 over 2x. And again, we've got to take 1 away. So that would give us 5 over 2. Negative times a positive is a negative, so that would give us 7 over 4x, and then again we want to take 1 away, so that would give us minus 9 over 2. And I mean, whoever would have thought, and I mean, this is why, you know, back in grade 7, grade 8, we always say fractions are so important, and it's because of this sort of situation now where you are using fractions in order to get to your answers. So if you can work quickly with fractions, that's great. If you can't, use your calculator. All right. Did you guys get the same answer as me?
Yes, ma'am.
Okay.
Yes.
Oh, good. All right. Everybody happy? Nice. Well done, Matrix. That's lovely. Good job. Okay, so we've got like 5 minutes left, right? So what I think I'm going to do is I'm going to save the really, look at these questions I've got for you down here. Look at those. Okay, but maybe what I'll do is I'll leave those for next time because I don't want to rush them. I definitely want to work through these more difficult ones with you as well. But in the last 5 minutes. Maybe what I should do is that. Hang on a second. Maybe we should all just do the same one rather than all of us doing different ones. Let's see what's a little bit, okay, tell you what, let's do G. Sure. Emily there, is that all right? Is that where you wanted me to go? I mean, in fact, if you guys could come back and work through all of these, that would be awesome, because I mean, the reason why I picked this one is because, again, you've got this letter here and you're not differentiating with respect to M, you're differentiating with respect to X. So, oh, to the previous question, that one. Sorted, Emily? Okay. All right. So I tell you what, for now, we can always come back and try more. Well, we've got time next time. We can come and work on a whole bunch of these. Just try and do G before you go. Oh, wow. Oratili, you finished already? Sure. Speedy Gonzalez, that's lovely. Sure, and Boucher. And Moronkhova, and Neo, and Maite, and Boychepo. Yeah, it certainly is, isn't it, Nicole? All right, so we've got a couple of minutes left. Nice, Emily. We can go through the answer before we say goodbye. So I guess what I would have done with this is I would have written it as x squared minus x to the half. And then because the bracket is squared, we've got to multiply that by itself. So if you wanted to, we could do the square double square thing again, but totally up to you if you don't want to do that. All right, now we've got to remove the brackets. All right, so doing FOIL now, we're going to end up with x to the power of 4. Okay, so that's first and first. First and second, when we multiply like bases, we subtract our, when we multiply like bases, we add our exponents. So that's going to be minus x, and then 2.5 is going to give us 5/2. This next term is going to be the same, so it's also going to be minus x to the power of 5/2, and our last term is going to be plus x to the power of 1. Okay, and then I think what I would do here is I would collect together my middle terms that are like terms, and I would have minus 2x to the power of 5/2 plus x. Now we're ready to differentiate. Dropping our dx, dropping our square brackets, we would end up with 4x cubed minus 5x to the power of 3 over 2 plus 1. Okay, do you agree? Do you guys get that as well?
Yes, ma'am.
All right, well done, Morongoa. Are there any questions? Lovely. Okay, well, I'm not going to do any more now. We're going to have a look at these questions again next time and try and do some of these more difficult ones, as well as those super difficult ones that I showed you down at the bottom. If you are happy and you want to go, you are more than welcome, and we will see you on Monday. Okay, so yeah, please do join us in the holidays so that we can continue with this.